Hello all. The topic which we'll be studying today is estimation of machining time for the subject machining principles and machine tools, code ME602, for the course of B.Tech third year 6th semester mechanical engineering course under MAKAUT. Now to start with instructional objectives. At the end of this lesson, we will be able to realize the necessity of evaluating the machining time requirement, identify the factors that govern the machining time, estimate or evaluate the time required for specific turning operation, drilling and boring operations, shaping and planing operations, milling operation. Now, necessity of estimation or determination of machining time requirement for particular operations. The main aim and objective in machining industry generally are reduction of total manufacturing time, increase in material removal rate or productivity, reduction in machining cost without sacrificing product quality, increase in profit or profit rate, that is profitability. All those objectives are commonly and substantially governed by the total machining time per piece given by TP, where again TP can be written as TI plus TC plus TC by TL into TCT, where TI is the idle time per piece, that is when the tool is not machining but it is being adjusted. TC is actual cutting time per piece. TL is tool life. TCT is average tool change time per piece. TI and TCT could have been spectacularly reduced by development and application of modern mechanization or automation. And also the tool life has been substantially enhanced by remarkable developments in the cutting tool material. Therefore, the actual cutting or machining time TC remains to be controlled as far as possible for achieving the objective and meeting the growing demands. Hence, it becomes extremely necessary to determine the actual machining time TC required to produce a job, mainly for assessment of productivity, evaluation of machining cost, measurement of labor cost component, assessment of relative performance or capability of any machine tool, cutting fluid, or any special or new techniques in terms of saving in machining time. The machining time TC required for a particular operation can be determined using two methods. First one, by roughly making calculation, that is estimation process, and secondly, precisely if required by measurement. Measurement definitely gives more accurate result and in detail, but is tedious and expensive, whereas estimation by simple calculations, though may not be that accurate, is simple, quick and inexpensive. Hence, determination of machining time, especially by simple calculations using suitable equations, is essentially done regularly for various purposes. Now coming on to major factors that govern machining time. The factors that govern machining time will be understood from a simple case of machining. A steel rod has to be reduced in diameter from D1 to D2 over a length L by straight turning in center lathe as indicated in figure 4.9.1. Here Tc, that is the cutting time, is given by Lc by N into S0 or S0 into Np, where Lc is actual length of the cut, which is given by L plus A plus O. A and O are the approach and overrun as shown in figure 4.9.1. Approach is the position where the tool is kept prior to complete any machining operation, and overrun is the length which the tool moves after the part has been cut. Here S0 is the feet given in millimeter per revolution, and Np is equal to number of passes required for the diameter to be reduced to D2 from D1. Speed is determined from cutting velocity Vc given by pi dn by 1000 meter per minute, where d is the diameter of the job before cut. Therefore, n or the RPM is given by 1000 into Vc cutting velocity by pi into d is the diameter of the workpiece. The number of passes Np is mathematically determined by Np is equal to d1 minus d2 divided by 2t. Here t is equal to depth of cut in one pass given in millimeters. Practically, the value of t and Np is decided by the machining allowance kept or left in the performed blanks. Usually, for saving time and material, very less machining allowance is left, if not almost eliminated by near net shape principle. Hence, number of passes used is generally 1 or maximum 2, one for roughing and one for finishing. However, combining equation 4.9.2, 4.9.4 and 4.9.5, one gets Tc is equal to pi dLc d1 minus d2 by 2000 Vc S0 T. And for single pass turning, Tc can be written as pi into d into Lc divided by 1000 into Vc into S0. Equation 4.9.7 clearly indicates that in turning to a given diameter and length, the cutting time, Tc is governed mainly by the selection of values of cutting velocity, Vc and S0. This is true more or less in all machining operations being done in different machine tools. A number of factors are essentially considered while selecting or deciding the values of VC and S0 for any machining work. The major factors considered for selecting VC are: first, nature of cut; second, work material, its type, strength, hardness, heat resistant, toughness, chemical reactivity, etc. Then cutting tool material, its type, strength, hardness, heat and wear resistant, toughness, chemical stability, thermal conductivity, etc. Then cutting fluid application, then purpose of machining, next kind of machining operation, next capacity of the machine tool, then condition of the machine tool. These are the factors which governs the cutting velocity. Now, the factors that are considered during selecting the values of feed are work material, type, strength, hardness, etc. Capacity of the machine tool, power, rigidity, etc. Cutting tool, material geometry configuration, cutting fluid application, surface finish desired, type of operation, for instance, threading operation needs large feed according to the lead of the thread. Nature of cut, that is the cut is continuous, shock initiated type or intermittent feed type, etc. Apart from the total volume of material to be removed, permissible values of cutting velocity, feed and depth of cut and cutting fluid application, there are few more factors which also play role in machining time. Those additional factors include quick return ratio in operation like shaping, planing, slotting, gear shaping, etc. Jobs of odd size and shape and regular and harder surfaces like large castings are essentially machined much slowly with lower cutting velocity. Some special techniques like hot machining and cryo machining enables faster machining of some exotic materials and even some common metals like steel at higher cutting velocity and feed rate. Now, estimation of machining time by calculation. The first case is turning on lathe. Figure 4.9.1 given in the previous slides and equation like equation 4.9.7 enable determination of the amount of time required for straight turning in lathe following the given procedural steps. Determine the length of cut by proper selection of amount of approach A, which ranges from 2 to 5 millimeters, and overrun O, which ranges from 1 to 3 millimeter if required. Select the approximate values of cutting velocity and feed based on the tool work materials and other factors previously mentioned. Determine the spindle speed and then fix N as well as feed from the chart giving the list of N and S0 available in the lathe. Finally, determine TC using equation 4.9.7, that is TC is given by pi d inside bracket LW plus A plus O divided by 1000 into VC into S0, as can be seen in the slide. Now coming on to an example. For diameter of 100 millimeter and length of workpiece 200 millimeter. Approach and overrun is selected to be 5 millimeter each. The cutting velocity is given by 120 meter per minute and feed is given as 0.2 millimeter per revolution. The cutting time is estimated to be 2.75 minutes. The machining time for facing, grooving, taper turning, threading, parting, etc. in lathe can also be determined or estimated following the same principle. Now, second case for drilling and boring. The basic principle and procedure of estimation of machining time in drilling and boring are almost same as that of turning operation. Figure 4.9.2 shows making through hole by drilling and boring. The figure is shown in the slide. For drilling a through hole, the machining time Tc is estimated from Tc is equal to Lc divided by N into feed, where Lc dash is equal to LH plus A plus O plus C. The different parameters shown over here can be identified in figure 4.9.2. Here C is given as D by 2 into cot rho, where D is the diameter of the hole and rho is equal to half of the drill point angle. The speed N and feed are selected in the same way as it is done in case of turning. Therefore, the drilling time can be determined from Tc is equal to pi d inside bracket LH plus A0 plus O plus C bracket close divided by 1000 into Vc into S0, that is feet. In the same way, Tc is determined or established in boring also, only the portion C is not included as boring tool doesn't involve a nose angle. For blind hole, only overrun O is excluded. Now, coming on to an example where diameter of the drill is given as 25 millimeter. The half of the drill point angle is given as 60 degree. Cutting velocity is 44 meter per minute. Length of the cut is 60 millimeter, length of the hole. Feed is given as 0.25 millimeter per revolution. And approach and overrun is given as 2 millimeter. The total cutting time in this case is estimated to be 0.5 minutes. A third case, machining time in shaping and planing. Machining time in shaping can be estimated using the scheme given in figure 4.9.3, which shows the length of the tool, work travel required to remove a layer of material from the top flat surface of a block in a shaping machine. Using figure 4.9.3 of the previous slide, the total machining time can be determined from the expression Tc is equal to Lw divided by Ns into S0, S0, that is the feet. where LW is the total length of the travel of the job, that is W plus A dash plus O dash, where W is the width of the job, A dash and O dash are the approach and overrun. NS is equal to the number of strokes per minute. S0 is the feed of the job. Now NS has to be determined from the equation of cutting velocity, that is VC is equal to NS by 1000 into LC inside bracket 1 plus Q, where VC is the cutting velocity, LC is the stroke length, LW is the length of the workpiece, A dash and O dash are approach and overrun, and Q is the quick return ratio, that is the time of return stroke divided by the cutting stroke. Therefore, NS is equal to 1000 VC divided by LC inside bracket 1 plus Q. Practically the speed that is available nearest to this calculated value is to be taken up. The values of VC and feed are to be selected or decided considering the relevant factors already mentioned in case of turn. An example is given for understanding this better. Now, machining time of planing operation in planing machine are also determined in the same way, because the only difference is that in planing machine, cutting strokes and feed travels are imparted to the job and the tool respectively, just opposite to that of a shaping machine. Beside that, though both shaping and planing are reciprocating type, planing machine may allow higher cutting velocity. Now the last topic is machining time in milling operations. There are different types of milling operation done by different types of milling cutters. Plain milling by slab milling cutters, end milling by solid but small end milling cutters, face milling by large face milling cutters. Now figure 4.9.4 shows the scheme of plain milling by a plain or slab milling cutter and indicates how the machining time is being calculated. Now following the figure, the machining time for plain milling, a flat surface can be determined as TC is equal to LC by SM for the job width when it is lesser than the cutting length. Here LC is given by LW plus A plus O plus D by 2, where LW is the length of the workpiece, A and 0 are approach and overrun, DC is the diameter of the cutter, SM is the table feed, S0 is the feed per tooth, ZC is the number of teeth of the cutter, and N is the cutter speed. Again N has to be determined from the cutting velocity equation, that is VC is equal to pi dn by 1000. VC and S0, that is feed, have to be selected in the usual way considering the factors stated previously. Since milling is an intermittent cutting process, VC should be taken lower of the recommended for continuous machining like turning. Feed should be taken responsibly low within 0.10 to 0.50 millimeters depending upon the tooth size, work material and surface finish desired. An example is given, an easy example is given. I think you will be able to solve this type of equations if they are given as such. In the same method as shown in the example, TC can be determined for end milling and face milling by proper selection of speeds and feeds depending upon the tool work materials and other relevant factors. Now this brings us to the end of the topic as well as the module. I hope you have liked the lecture, and I sincerely hope that you will be giving me an honest feedback, and if you have any sort of doubts and all, kindly ping it to me on WhatsApp or you can call me. Thank you.